So it has magnitude and direction. We will get to the direction part a little bit later. We're not going to talk about that so much here at the beginning, but it is the angle formed with the positive x-axis. So we're staying with our convention of how we measure angles being with the positive x-axis. So I've got an example of a vector there. Let's label the parts just so that we know the terminology here. This would be the initial point. And this is the terminal point. So if we call our initial point P and our terminal point Q, then our vector here is named PQ, and it has a symbol over the top of it. It's not a full arrow. It only has one side of the arrow on the end there, but that is your vector notation there. You may also see it as a bold lowercase letter. So in this case, we'll just use V for vector. A lot of times they use U and V for that, but it will be a bolded letter to name it as well. So obviously, the longer the vector is, the greater the magnitude. The whole purpose of vectors we will get to eventually is to represent a lot of forces. Okay, if any of you end up taking physics or a class like that in college, you will deal with vectors, and vectors are always used to represent forces. All right, so we need to be able to break these vectors down into what we call component form. So if we have the initial point P, we already labeled on our picture there, say that it has the coordinates P sub 1 and P sub 2. Okay, those are representing an X and a Y coordinate. Okay, they are representing an X and a Y, but we just name them with the subscripts. And then we have our terminal point Q, same thing. That is an X and a Y. We just name it with the subscripts when we talk about our vectors here. So to find the component form of the vector, we subtract the x's, q1 minus p1. That's what you see right here. We subtract the x components, we subtract the y components, and we get these quantities right here, v sub 1 and v sub 2. Notice with the vector that we don't put parentheses around it. Parentheses indicate that it's a point. A vector, we use these pointy brackets around the two quantities to represent that that is indeed a vector and it's not a point. Okay, so then we can find the magnitude once we have subtracted our x's, subtracted our y's to get the component form. Then we can find the magnitude of our vector by taking the square root of the x component squared plus the y component squared. Really where all this is coming from is if we have a vector here, we can really form a right triangle. This would be its x component, this would be its y component, and the length of the vector is the magnitude. So if we have a right triangle right there, and we know v sub 1 and v sub 2, we know the legs, then what can we apply? The Pythagorean theorem. That's where this formula for magnitude is coming from. Square the legs, add them together, take the square root, you have the hypotenuse. Well, in this specific application of it, the hypotenuse is the magnitude. All right, so let's actually apply these formulas here. Okay, find the component form and magnitude of the vector that has initial point 4, -7 and terminal point -1, 5. So if you need to label them, P sub 1, P sub 2, Q sub 1, Q sub 2. It's not really particularly necessary, but if you would rather That is fine. I'm going to show the work the first few times just so that when you look back, you know what happened. -1 minus 4, comma, 5 minus -7. And really, just like with slope, because that's kind of what we're doing here, subtracting the x's, subtracting the y's, the order technically doesn't matter. I could do 4 minus -1. I'm going to get the same number. We're going to get -5, and we're going to get positive 12. Okay, so that's the component form, -5, positive 12 is the component form. Let's find the magnitude. Okay, it looks like double absolute value bars. And then that's the square root of your x squared plus your y squared. Now, personally, when I'm doing this, to avoid making the mistake of forgetting my parentheses, you know that a negative number squared is always positive, so don't even put it, okay? Don't even put it in your problem there. 5 squared plus 12 squared is 13. So the magnitude of this vector is 13, and the component form is -5, positive 12. Let's do another one. Initial point, -2, 3. Terminal point, -7, 9. So let's find the components. I'm going to just reverse the order to show you that it really doesn't matter. This time I'm going to do the one that's given first minus the one that's given second. So -2 minus a -7. Either way you subtract it, it's going to give you positive 5. Oh, no, wait. The order does matter. Sorry. That was not a true statement. The order does matter. You do have to do the second one minus the first one. I was not looking on that. When you add, it doesn't matter. When you subtract, it most certainly does. My bad. -7 minus -2 is -5. 9 minus 3 is positive 6. My apologies. Okay, so our magnitude here is the square root of -5 squared plus 6 squared. This time, I don't think we're going to end up with a perfect square. So I'm going to leave the square root off to begin with. Yeah, 61 is not a perfect square. And I don't believe it's divisible by any perfect squares. So we'll just leave it as the square root of 61. The reason why the order does matter, I was just thinking about this, y'all. The reason why the order does matter is it will be pointed in the opposite direction if you switch the order between the initial point and the terminal point. So you do always have to do terminal minus initial. Okay, it does always have to be terminal minus initial.